On August 15, 1977, at exactly 10:39 in the evening, a radio telescope in Ohio detected something impossible. A signal so strong, so precise, so unmistakably artificial that the astronomer who found it grabbed a red pen and wrote a single word in the margin of the printout. Wow, that signal came from deep space. It lasted exactly 72 seconds. And then it vanished. We've been searching for it ever since. We've never heard it again. This is the story of the most compelling evidence we've ever found that we're not alone in the universe, and the maddening mystery of why it only happened once. If understanding humanity's closest brush with contact sounds worthwhile, a quick subscribe would mean the world to me, and drop a comment letting me know where you're watching from. Let's explore the message we received and lost. To understand the wow signal, you need to picture where it came from and who found it. The Big Ear radio telescope sat in the flat farmland outside Delaware, Ohio. It wasn't like the big dish telescopes you might imagine. Big Ear was enormous. It covered an area about the size of 3 football fields. But instead of a movable dish that could point at different parts of the sky, Big Ear was fixed. 2 flat rectangular reflectors on the ground bounced radio waves up to a curved reflector overhead, which focused them into receivers. The telescope couldn't turn or move, it just sat there. As Earth rotated, different parts of the sky drifted through Big Ear's field of view. This meant any signal from space would pass through the telescope's view for exactly 72 seconds before Earth's rotation carried it out of range. That 72-second window becomes important. Big Ear was run by Ohio State University. It was part of SETI, the search for extraterrestrial intelligence. The idea was simple: listen to the sky with radio telescopes, look for signals that don't match natural sources, hope that somewhere out there someone is broadcasting. Every few days, someone would drive out to the observatory and collect the computer printouts, reams of paper covered in numbers and letters. Each character represented the intensity of radio waves detected at different frequencies. Most of the time, the printout showed noise, random static from natural sources, stars, galaxies, cosmic background radiation, just the universe humming to itself. But occasionally, something would stand out. On August 15, 1977, Big Ear was pointed toward the constellation Sagittarius. The telescope scanned through different radio frequencies, listening for anything unusual. At 10:39 p.m., it detected a signal. A very strong signal. The signal peaked at 30 times louder than the background noise. That's an enormous spike. In the realm of radio astronomy, anything more than 3 times the background noise is worth investigating. 30 times is extraordinary. The signal appeared on our very specific frequency, 1420 megahertz. This frequency is significant for reasons we'll get into. The signal lasted exactly 72 seconds. It rose in intensity, peaked, then faded away as Earth's rotation carried Big Ear's view past the source. The pattern matched exactly what you'd expect from a stationary source in space drifting through the telescope's field of view. A few days later, Jerry Amon, a volunteer astronomer working on the SETI project, was reviewing the printouts. He was sitting at his home, going through page after page of data. mostly boring, mostly noise. Then he saw it. A column of characters that didn't look like anything else on the page. The intensity was represented by a code. Numbers from 1 to 9 represented increasing signal strength. After 9, the code switched to letters, A, B, C, and so on. The stronger the signal, the further along in the alphabet. Eamon saw the sequence 6EQUJ5. That J represented a signal, strength he'd never seen before. He grabbed the red pen he used to mark interesting finds, and he wrote in the margin, circling the sequence, the word "wow" with an exclamation mark. Not a technical notation, not a formal designation, just a raw human reaction to seeing something astonishing. That red circle and that word gave the signal its name, the WOW signal. Let's break down what 6EQUJ5 means. Each character represents the signal intensity for a 12-second interval. The computer recorded data in 12-second chunks. The sequence shows the signal ramping up, peaking, then falling. The 6 means the signal was 6 times louder than background noise. Then E, which is 14 times louder. Then Q, which is 26. Then U, which is 30. That's the peak. Then J, which is 19 times. Then 5, back down to 5 times. Then nothing. The signal rose, peaked at 30 times background, and faded all within 72 seconds. The smooth rise and fall, the perfect timing. Everything suggested this was a point source, something stationary in space. As Big Ear's field of view swept past it, the signal came into view, crossed the center of the beam where detection was strongest, then passed out of view. Exactly what you'd expect from a distant transmitter. Now, here's where it gets interesting. The frequency matters enormously. 1420 megahertz is right in the middle of what's called the hydrogen line. Hydrogen is the most abundant element in the universe. When hydrogen atoms flip their electron spins, they emit radio waves at a very specific frequency, 1420.4 megahertz. Every astronomer in the universe would know about the hydrogen line. It's a universal constant. If you wanted to send a signal that other civilizations might notice, you'd broadcast near the hydrogen line. It's like putting a billboard on the busiest highway in the cosmos. Everyone's already looking there. The WOW signal wasn't exactly on the hydrogen line. It was close, about 1420 megahertz. That slight offset might be deliberate, to distinguish an artificial signal from natural hydrogen emission. Or it might be due to the Doppler shift. If the source was moving relative to Earth, the frequency would shift slightly. Either way, the fact that the signal appeared near the hydrogen line immediately made it more interesting. There's another detail. The signal was narrowband, very narrowband. Natural sources of radio waves tend to be broadband. They emit across a range of frequencies. Stars, galaxies, pulsars. They all spread their energy across the spectrum. But the WOW signal was concentrated in a very narrow frequency range, less than 10 kilohertz wide. This is characteristic of artificial transmitters. When you build a radio transmitter, you focus the energy into a specific frequency. It's more efficient. You get a stronger signal. Natural processes don't do this. They're messy, spread out. The narrow band nature of the wow-wow signal was one of the strongest indicators that it might be artificial. It matched what SETI researchers were looking for: a strong, narrow band signal near a significant frequency. The wow-wow signal checked all the boxes. Jerry Amon knew immediately this was important. He contacted the other researchers working on the project. They looked at the data. They confirmed the spike. They checked for errors. Could this be a glitch? A malfunction in the equipment? They ruled that out. The telescope was working normally. They checked for human interference. Could this be a transmission from Earth, a satellite, an airplane? They checked the frequency. 1420 megahertz is in a protected band. It's illegal to transmit at that frequency. It's reserved for radio astronomy to prevent exactly this kind of contamination. No commercial or military transmission should appear there. They checked satellite records. Nothing was overhead at that time. They checked aircraft. Nothing in the area. Every obvious explanation failed, so they did what any scientist would do. They tried to observe it again. If the signal was real, if it was coming from a fixed point in space, they should be able to point the telescope back at that location and hear it again. Big Ear couldn't move, but Earth rotates. The same part of the sky comes back into view every 23 hours and 56 minutes. One sidereal day. So, the next night, at roughly the same time, the researchers monitored the telescope. They watched as that region of Sagittarius came into Big Ear's view. They waited. Nothing. No signal. They tried again the next night, and the next, and for weeks and months afterward. They pointed other telescopes at the same coordinates. Still nothing. The signal was gone. It had appeared once for 72 seconds and then vanished. To this day, despite thousands of hours of follow-up observations, despite checking with more sensitive equipment, despite searching with telescopes all over the world, we've never detected it again. This is the central mystery of the wow-wow signal. If it was a natural phenomenon, why hasn't it repeated? Natural sources like pulsars or flare stars emit regularly. You can predict when they'll go off. You can observe them again and again. But the wow-wow signal only happened once. If it was human-made interference, why did it appear at a protected frequency? Why did it match the signature of a distant point source? Why did it last exactly 72 seconds? The time it takes for a fixed source to drift through Big Ear's beam. And if it was aliens, why did they only transmit once? Why have we never heard from them again? These questions have haunted researchers for over 4 decades. The wow signal remains one of the most compelling and frustrating mysteries in the history of SETI. To appreciate why the wow signal matters, you need to understand what SETI is and what researchers are trying to do. The search for extraterrestrial intelligence is based on a simple premise. If intelligent life exists elsewhere in the universe, and if that life develops technology, they might communicate using radio waves. Radio waves are efficient. They travel at light speed. They penetrate dust and gas. They're relatively easy to generate and detect. An advanced civilization might use radio to send messages between their planets, between their spacecraft, or deliberately into space as a beacon. If we listen carefully, we might pick up those transmissions, either accidental leakage from their everyday communications or intentional signals meant to be found. SETI began in 1960 when astronomer Frank Drake conducted the first search, Project Ozma. He pointed a radio telescope at two nearby stars and listened for signals. He didn't find anything, but he established the methodology. Since then, SETI has grown. More telescopes, better receivers, more sophisticated analysis. Researchers scan the sky, systematically listening across many frequencies, looking for anything that stands out. Most of what they hear is noise. The universe is loud. Stars emit radio waves. Galaxies emit radio waves. Cosmic microwave background radiation fills space. Separating a possible artificial signal from all that natural noise is incredibly difficult. But occasionally, something catches their attention. A spike, an anomaly, something that doesn't fit the pattern, and they investigate. The famous Drake equation tries to estimate how many communicating civilizations might exist in the galaxy. It multiplies several factors: the rate of star formation, the fraction of stars with planets, the number of planets per star that could support life, the fraction where life actually emerges, the fraction where life becomes intelligent, the fraction that develops technology, and the length of time such civilizations broadcast. Multiply all these together and you get an estimate. But we don't know most of these numbers. We can guess. We can make optimistic or pessimistic assumptions. Depending on what you plug in, the Drake equation says we might be alone or the galaxy might be teeming with civilizations. The WOW signal, if it was artificial, would tell us that at least one of those factors is higher than zero. Someone out there is broadcasting, or was broadcasting, and we heard them, however briefly. Let's talk about the natural explanations people have proposed for the WOW signal. Because when you detect something anomalous, your first instinct as a scientist is to explain it with known phenomena. Maybe it's not aliens. Maybe it's something mundane we didn't think of. The first obvious possibility is satellites. Could a satellite have passed overhead at the right time and transmitted at 1420 megahertz? This seems plausible until you check the details. First, that frequency is protected. Satellites don't transmit there. Second, satellites move. If a satellite was the source, the frequency would shift due to Doppler effect. The satellite's motion toward or away from the telescope would compress or stretch the radio waves, changing the observed frequency. Big Ear's receivers would have detected this shift. They didn't. The signal stayed at a constant frequency. Third, satellites pass through the telescope's view quickly, maybe a few seconds, not 72 seconds. The duration matches a fixed astronomical source, not a moving satellite. What about aircraft? Could a plane have flown over at the right moment? Again, the details don't fit. Aircraft transmitters, like satellite transmitters, are not allowed at 1420 megahertz. And aircraft move fast. The signal would Doppler shift. It would sweep across frequencies as the plane approached and receded. Big Ear would have seen a changing frequency, not a stable one. Plus, the telescope's view is narrow. A plane would have to fly precisely through that narrow cone at exactly the right altitude and exactly the right time to produce a 72-second signal. Possible, but incredibly unlikely. And it would have had to be broadcasting at an illegal frequency with no identifiable transponder. Every air traffic database from that night has been checked. No aircraft were in the area that could explain the signal. Could it have been a reflection? Maybe a terrestrial transmitter bounced off something, an airplane or a piece of space debris, and reflected into Big Ear's receivers. This is a known phenomenon. Radio signals can bounce off objects and arrive from unexpected directions. But, again, the details argue against it. The signal was at a protected frequency. What ground transmitter would be broadcasting there? And reflections distort signals. They add noise. They spread the frequency. The wow signal was clean, narrowband, strong, not the messy signature of a reflection. And for a reflection to produce a 72-second signal with the exact rise and fall pattern matching a point source, the geometry would have to be perfect. The reflecting object would have to move at just the right speed and angle to create that pattern. It's not impossible, but it requires an extraordinary series of coincidences. Then there's the idea that it was a transmitter on Earth in the direction Big Ear was looking. If a transmitter on the ground happened to be in the line of sight when the telescope was aimed at Sagittarius, it could produce a signal that appeared to come from space. This is possible, but again, who's transmitting at 1420 megahertz? It's illegal. And why would they transmit for exactly 72 seconds? And why haven't they transmitted again in the 40-plus years since? Every follow-up search has checked that region of the sky. If there's a ground transmitter there, it should have been detected again. It hasn't. This explanation requires that someone illegally transmitted at a protected frequency for exactly 72 seconds, never did it again, and nobody ever found the transmitter, despite decades of searching. That's a lot of coincidences. In 2017, astronomer Antonio Paris proposed a new explanation. He suggested the WOW signal came from a comet, specifically two comets, 266P Christensen and P 2008Y2, that was in the area of sky Big Ear was looking at on August 15, 1977. Comets have clouds of gas around them called comas. These comas contain hydrogen. When hydrogen is excited by solar radiation, it can emit at the hydrogen line frequency. Paris argued that Big Ear detected this hydrogen emission from a comet's coma. It would be a natural source. It would be transient. It would explain why we haven't heard it again. The comets moved. They're no longer in that location. Problem solved. Except this explanation has serious issues. First, comet comas emit radiation across a broad range of frequencies, not the narrow band detected in the WOW signal. The signal was less than 10 kilohertz wide. Comet emissions are much broader. Second, the intensity. The WOW signal was 30 times louder than background noise. Comet comas are diffuse. The hydrogen emission is spread over a large area. It would be weak. To produce a signal 30 times above background would require an extraordinarily bright comet, brighter than any comet observed before, and nobody noticed such a bright comet in 1977. Astronomers observe comets constantly. A comet bright enough to produce the WOW signal would have been noticed. Third, the location. When researchers checked the comet orbits, the comets Paris identified were not in Big Ear's beam at the exact time of the WOW signal. They were nearby, within the same general region of the sky, but not precisely where the signal came from. Big Ear's beam was narrow, a few arc minutes. For the comet explanation to work, the comet had to be right in the center of the beam at the exact moment. And it wasn't. Moreover, if comet comas routinely produce signals like this, we should have detected others. Big Ear operated for years. Other radio telescopes have scanned the sky for decades. We've observed thousands of comets. Where are the other WOW-like signals? They don't exist. The WOW signal is unique. The comet explanation tries to explain it away as a common phenomenon we just happen to catch once. But if it's common, we should see it often. We don't. Jerry Amon himself, the astronomer who discovered the signal, was skeptical of the comet explanation. He pointed out the problems. He said that while he couldn't rule it out completely, it didn't fit the data as well as people claimed. The comet explanation became popular because people want an answer. They want closure. But wanting an answer doesn't make a bad answer good. The comet explanation is possible but problematic. It raises as many questions as it answers. So, what do we know for sure about the WOW signal? We know it happened. The data is real. It's not a hoax or a mistake. The telescope detected a strong radio signal at 1420 MHz on August 15, 1977 at 10:39 p.m., coming from the direction of Sagittarius. The signal lasted 72 seconds and peaked at 30 times background noise. It was narrow band, less than 10 kHz wide. It matched the profile of a point source drifting through the telescope's beam. These are facts. Documented, verified. The signal was detected by both of Big Ear's receivers independently. It wasn't a glitch in one receiver. Both saw it. This redundancy is important. It confirms the signal was real. We also know that despite thousands of hours of follow-up observations, no one has detected it again. Multiple telescopes have searched the same region of sky. More sensitive instruments have been used. Broader frequency ranges have been scanned. Nothing. If the signal came from a persistent source, whether natural or artificial, it should still be there. If it came from an intermittent source, we should have caught it again by now, with so many observations. The silence is as mysterious as the original detection. It tells us that whatever the source was, it was either one time, incredibly rare, or has since moved, shut off, or changed in some way we don't understand. We know that the signal fit the criteria SETI researchers were looking for: strong, narrow band, near a significant frequency. These characteristics make it interesting. They match what an artificial signal might look like, but they don't prove it was artificial. Natural phenomena can occasionally mimic artificial signals. Pulsars, for instance, produce regular pulses of radio waves that initially seemed so artificial they were nicknamed LGM for little green men. But pulsars are natural. They're spinning neutron stars. The WOW signal could be something similar. a natural phenomenon we don't understand, something rare, something that only happens under specific conditions. But if that's the case, what is it? What natural process produces a strong, narrow-band, transient signal at the hydrogen line? We don't have a good answer. That's the frustration. We can't definitively say it was artificial, but we can't explain it naturally either. It exists in this uncertain space, anomalous, unexplained, tantalizing. The question everyone asks is, what if it really was aliens? What would that mean? Let's think through this carefully. If the wow signal was an intentional transmission from an extraterrestrial civilization, it tells us several things. First, we're not alone. Somewhere out there, in the direction of Sagittarius, roughly 78 light-years away, based on where the signal appeared to originate, there's someone with technology advanced enough to build powerful radio transmitters. They exist. They're broadcasting. We heard them. That would be the most profound discovery in human history. It would fundamentally change how we see ourselves and our place in the universe. We'd no longer be the only intelligence. We'd be one among many. Second, if they're broadcasting at the hydrogen line, they're sophisticated. They understand radio astronomy. They know that other civilizations would monitor that frequency. This suggests they want to be heard. They're sending a beacon, or at least they were on August 15th, 1977. The signal might have been part of a regular broadcast schedule. Maybe they send a pulse every few hours or days, and we just happened to catch one 72-second window. Or maybe they scan the galaxy. They rotate their transmitter, aiming at different stars, sending brief signals to each one. We got our turn. Then the beam moved on. We haven't heard it again because they're not pointed at us anymore. Or maybe the civilization is gone. The signal was sent 78 years ago. It took that long to reach us traveling at light speed. 78 years is nothing in cosmic terms, but a lot can happen. Wars, natural disasters, technological collapse, self-destruction. They might have existed in 1999 when the signal was sent and perished since then. Third, if the signal was artificial, it raises questions about their intentions. Were they trying to communicate, or was this leakage? Accidental radiation from their technology that we happened to pick up. If they were trying to communicate, the signal itself doesn't contain much information. It's just a spike, a carrier wave, no modulation, no pattern, no data embedded in it. It's like someone keying a microphone on and off. You know someone's transmitting, but they're not saying anything. Maybe the point was just to get noticed. A simple hello. Once you detect the carrier, you're supposed to look more carefully. Search for follow-up transmissions with actual content, messages, data. But we've looked and found nothing. So either we missed the follow-up, or there wasn't one, or it was sent in a way we don't recognize. The geometry of the signal is interesting too. Big Ear had two beams. Two separate receiver horns pointing at slightly different patches of sky. Both detected the signal at the same time. This tells us the signal was broad enough to cover both beams. The beams were separated by a few arc minutes, so the source had to be either very large or very distant with a broad transmission pattern. For a point source transmitter, the signal would need to be powerful to illuminate that much sky. We're talking about serious energy, megawatts or gigawatts. An advanced civilization could certainly build such a transmitter. But why? Why use so much power for a brief signal? Maybe because they're far away and they need the signal to be strong enough to be detected across interstellar distances. Or maybe they're not far away and the broadcast is omnidirectional, sent in all directions equally. That would be less efficient, but it ensures everyone in a large region of aided space can hear it. There's also the question of when the signal was sent. If the source is 78 light years away, the signal took 78 years to reach us. It was transmitted in 1899. That's a strange time. Earth was just beginning the modern industrial age. Radio had just been invented. Marconi was experimenting with wireless communication. If an alien civilization was monitoring Earth from 78 light years away, they wouldn't have seen any signs of our technology yet. The light and radio waves from Earth's early industrial age wouldn't have reached them until decades later. So, if they were sending a signal to us specifically, they were doing it blind. They wouldn't have known we existed as a technological civilization. They were just broadcasting to a star system that might have planets that might have life, a speculative beacon. Or the signal wasn't meant for us at all. It was meant for someone else, or no one, just a transmission from their everyday activities that we accidentally intercepted. The timing is curious for another reason. 1977 was early in SETI's history. We'd only been seriously looking for a few years. What are the odds that we'd detect a signal in one of our first real attempts? It's like fishing in a vast ocean and hooking something on your third cast. Either we're incredibly lucky or signals are more common than we think. If signals are common, we should have detected more by now. We've been listening for over 40 years with much better equipment. Where are the others? This is the frustration. The WOW signal tantalizes us with the possibility of contact, but then leaves us hanging. One detection, no follow-up, no confirmation, just enough to suggest something's out there, but not enough to prove it. Let's talk about how radio astronomy actually works, because understanding the technical details helps appreciate why the WOW signal is so remarkable. Radio telescopes don't produce images like optical telescopes. They don't show you pictures of planets or galaxies. Instead, they detect radio waves and measure their intensity and frequency. When you point a radio telescope at the sky, you're essentially sampling the electromagnetic spectrum in the radio range. You pick a frequency or range of frequencies, and you measure how strong the signal is at each moment. The output is data, numbers. How many watts per square meter per hertz of radio energy are arriving from that direction at that frequency? To search for artificial signals, you need to filter out all the natural sources. The universe is full of radio noise, cosmic microwave background, synchrotron radiation from electrons spiraling in magnetic fields, thermal emission from gas and dust. Every star emits some radio waves, every galaxy, every nebula. All of this creates a background hum. Most of the time, when you point a radio telescope at the sky, you hear this hum. It varies a bit from place to place and frequency to frequency, but it's always there. An artificial signal would have to stand out above this background. It would have to be stronger, narrower, or patterned in some way that natural sources aren't. Big Ear's receivers sampled the sky in 50 channels simultaneously. Each channel covered 10 kilohertz of bandwidth. So, Big Ear was listening to 50 different slices of the spectrum at once. Each channel produced a data point every 12 seconds. The printout Jerry Amon looked at showed these data points as characters. The strength of the signal in each 12-second interval represented by a number or letter. Most of the page was zeros and ones. Quiet. Occasionally a 2 or 3 when something slightly brighter passed through. But 6QBJ5, that sequence stood out. Those numbers and letters were far higher than anything else on the page, higher than anything Echgarn had seen in all the hours he'd spent reviewing data. That's why he reacted the way he did. It was unmistakably anomalous. The verification process for signals like this is crucial. You can't just see one spike and declare you found aliens. You need to rule out mistakes, equipment malfunctions, interference, natural phenomena. The first check is redundancy. Big Ear had 2 receiver horns. They both detected the signal. That rules out a malfunction in one receiver. The signal was real. Both receivers saw it. The second check is frequency. What frequency was the signal at, and is that frequency consistent with what you'd expect from a distant source, or does it match interference? The wow signal was at 1420 megahertz. Protected band. No terrestrial interference expected. Good sign. Third check, duration. Does the duration match what you'd expect from a fixed source drifting through your telescope's field of view? 72 seconds for Big Ear. The WOW signal was 72 seconds. Perfect match. Fourth check. Does the signal repeat? If it's a fixed source, whether natural or artificial, it should still be there. Point your telescope back and see if it's still transmitting. The WOW signal didn't repeat. That's the anomaly. It breaks the pattern. When signals don't repeat, it makes verification almost impossible. You're left with a single data point. You can analyze it. You can confirm it was real. But you can't study it further. You can't determine if it's artificial or natural with certainty. This is why astronomers are cautious about claiming detection of extraterrestrial intelligence. You need repeatable, verifiable data. One signal is intriguing but not conclusive. The scientific standard is extraordinary claims require extraordinary evidence. The WOW signal is extraordinary, but one detection, no matter how compelling, doesn't meet the threshold for proof. It's evidence, strong evidence, but not proof. Since the WOW signal, there have been other candidate signals, other brief anomalies detected by radio telescopes. Each one gets investigated. Each one turns out to be something mundane or remains unexplained without enough data to conclude anything. In 2020, the Parkes telescope in Australia detected a signal called BLC1, Breakthrough Listen Candidate 1. It appeared to come from the direction of Proxima Centauri, the nearest star system to Earth. It was narrowband. It had characteristics that matched what you'd expect from a transmitter. Excitement built, but follow-up observations showed the signal was terrestrial interference, a periodic signal from human sources that mimicked an extraterrestrial one. This is the challenge. Earth is awash in radio transmissions, cell towers, satellites, radar, Wi-Fi. All of this creates a noisy electromagnetic environment. distinguishing genuine signals from space from this terrestrial cacophony is hard. Most candidate signals turn out to be interference. Fast radio bursts, FRBs, are another phenomenon that briefly sparked speculation. These are intense bursts of radio energy lasting milliseconds. They come from distant galaxies. Their origin was a mystery for years. Some suggested they might be artificial, perhaps energy beams from alien propulsion systems or megastructures. But recent observations have traced FRBs to magnetars, extremely magnetic neutron stars. When a magnetar's magnetic field reconfigures suddenly, it releases a burst of energy. That's what we're seeing. FRBs are natural, not artificial. This is usually how it goes. Something anomalous is detected. People speculate. More data is gathered. A natural explanation emerges. The universe is full of strange phenomena. Most turn out to be natural, even if they're initially puzzling. The wow signal stands out because it's resisted explanation for so long. Over 40 years, and we still don't have a satisfying answer. It's not obviously interference. It doesn't fit known natural phenomena. It's not obviously artificial either because it didn't repeat. It's stuck in limbo. The best candidate, signal we've ever detected, but not strong enough to confirm, just strong enough to haunt us, to make us wonder, to keep us searching. Jerry Amon, the man who discovered the signal, lived the rest of his life with this mystery. He gave talks about it. He answered questions. He reviewed every proposed explanation. He remained cautiously optimistic that it might have been extraterrestrial, but he never claimed certainty. He said in interviews that he hoped someone would find a natural explanation, because without one, we're left wondering, and wondering is uncomfortable. Scientists like closure. They like answers. The wow signal doesn't offer that. It's an open question, a puzzle with missing pieces. Amon passed away in 2020. He never got the answer he was looking for. The signal remained unexplained. His approach to the mystery is instructive. He didn't leap to conclusions. He didn't claim he'd found aliens despite finding the most compelling evidence ever. He remained skeptical, critical, open-minded. He acknowledged the possibility but didn't overstate it. This is scientific integrity. Wanting something to be true doesn't make it true. The data has to support the conclusion, and the data on the wow signal is ambiguous. It could be artificial. It could be natural. We don't know. That uncertainty is frustrating, but it's honest. Better to admit you don't know than to claim knowledge you don't have. The story of the WOW signal also highlights how fragile our search for extraterrestrial intelligence is. Big Ear operated from 1963 to 1998. 35 years of scanning the sky. Then it was demolished. The land was needed for development. A golf course. The telescope is gone. We can't go back and re-observe with the same instrument. We can use other telescopes, but they're different. Different sensitivities, different beam patterns, different characteristics. If the signal was something specific to Big Ear's design, something about how it interacted with that particular telescope, we might never understand it. The loss of Big Ear is a loss for SETI. We have better telescopes now, but We don't have that specific instrument anymore. This speaks to a broader issue. SETI is chronically underfunded. For most of its history, it's relied on volunteers and small grants. NASA briefly funded SETI in the early 90s, but Congress cancelled the funding after 1 year. Since then, SETI has been privately funded. Organizations like the SETI Institute and Breakthrough Listen, funded by philanthropist Yuri Milner, keep the search going. But the resources are limited compared to other fields of astronomy. We spend billions on space telescopes to study galaxies and exoplanets. We spend millions on SETI. The imbalance reflects priorities. Most astronomers don't think SETI is likely to succeed. They think intelligence in the universe is rare or non-communicative. So funding goes to other questions more likely to yield results. But the wow signal suggests maybe they're wrong. Maybe intelligence is out there. Maybe we're not looking hard enough or in the right way. If we'd been monitoring the sky more continuously, with more telescopes covering more frequencies, maybe we'd have detected the wow signal multiple times. Maybe we'd have caught follow-up transmissions. But we weren't. Big Ear was scanning. It covered a small part of the sky at any given time. It caught the signal by chance. What else have we missed? How many signals have passed through our solar system undetected because we weren't looking at the right place at the right time? We can't know. The universe is big. Our monitoring is sparse. We're sampling tiny fractions of the sky for tiny fractions of time. It's like scooping a cup of water from the ocean and concluding there are no fish because you didn't catch any in your cup. The development of new technologies gives us hope. Modern radio telescopes are far more powerful than Big Ear. The Very Large Array in New Mexico, the Arecibo Telescope in Puerto Rico before it collapsed, the Green Bank Telescope in West Virginia, the Square Kilometre Array being built in Australia and South Africa. These instruments can detect fainter signals over broader frequency ranges. They can scan larger areas of sky simultaneously. If the WOW signal repeats, if whoever or whatever sent it transmits again, we have a better chance of detecting it now than we did in 1977. But better isn't guaranteed. We still need to be pointed in the right direction at the right time on the right frequency. The odds are against us, but they're better than they used to be. There's also been a shift in strategy. Early SETI focused on monitoring nearby stars. The idea was that civilizations would be on planets orbiting stars similar to our Sun. So we'd listen to those stars, hoping to catch their communications. But we've realized that signals can come from anywhere, not just planetary systems. Maybe from spacecraft traveling between stars, maybe from structures in deep space. So modern SETI casts a wider net. Scan the whole sky. Look for anything anomalous. Don't limit yourself to predefined targets. This approach is more likely to catch unexpected signals like the WOW signal, but it generates more data, more false positives, more noise to filter through. The challenge is developing algorithms and AI systems that can identify interesting signals automatically. Humans can't review every data point. There's too much. We need machines to flag potential candidates for human review. Breakthrough, Listen, One of the most ambitious SETI projects currently running is doing exactly this. They're using some of the world's most powerful telescopes to scan millions of stars and thousands of galaxies. They're recording unprecedented amounts of data, and they're developing machine learning algorithms to analyze it. The idea is to catch anything unusual, any signal that doesn't fit natural patterns, then investigate further. It's a brute force approach. Listen to everything. Let computers sort through it, see what turns up. In the few years Breakthrough Listen has been operating, they've found thousands of candidate signals. So far, none have panned out. They've all been interference or natural sources. But the search continues. Every observation adds to our knowledge. Every false positive helps refine the algorithms. Eventually, if there's a signal to find, this approach might find it. But there's a philosophical question underlying all of this. Should we be searching at all? Some argue yes, absolutely. The potential payoff is enormous. Confirming we're not alone would reshape human civilization. It would answer one of the oldest questions. Are we special, unique, or just one example among many? The answer would affect philosophy, religion, science, culture, everything. Even a negative result has value if we search thoroughly and find nothing. That tells us something too. It suggests intelligence is rare. Maybe we're among the first. Maybe we have a unique role. Either answer matters. Others are more cautious. They worry about the risks of contact. What if we attract attention we don't want? What if there are hostile civilizations out there? Broadcasting our presence might be dangerous. This is the dark forest hypothesis. The idea that the galaxy is full of civilizations hiding from each other because the risks of contact are too high. The first rule of survival is, don't make noise. Don't let predators know where you are. Maybe the wow-ow signal was a mistake. Some civilization accidentally revealed themselves. And now they're silent again because they realize their error, or because something found them. This is speculation. We have no evidence of hostile aliens, but we have no evidence of friendly ones either. The uncertainty makes some people nervous. The reality is we're probably already detectable. Earth has been leaking radio and television signals into space for about a century. Any civilization within 100 light years with sensitive enough receivers could detect us. We've been announcing our presence whether we intended to or not. The signals are weak by the time they propagate that far, but they're there. So the question of whether to broadcast is somewhat moot. We already are. The real question is whether we actively send stronger, more deliberate messages. ME-TE, messaging extraterrestrial intelligence, is the term for this. Some researchers think we should, others think it's reckless. The debate continues. For now, most of our efforts are focused on listening, not transmitting. The WOW signal, if it was artificial, shows that listening can work. Someone might be out there broadcasting. We just need to catch them. There's something deeply human about the search for extraterrestrial intelligence. It reflects our curiosity, our desire to explore and understand, our need to know if we're alone. These are fundamental questions. They've been asked for thousands of years. Ancient philosophers wondered if other worlds existed, if other beings lived on them. Now we have the technology to actually look, to search systematically, to potentially get an answer. That's remarkable. We're living in a unique time. The first generation that can seriously search for extraterrestrial intelligence. Previous generations could only speculate. Future generations might know the answer. We're in between, searching, waiting, hoping. The wow-ow signal embodies this moment. It's a tantalizing hint, not an answer, but a clue. It suggests that maybe, just maybe, someone's out there. Someone transmitted something. We caught it. We don't know who. We don't know why. We don't know if we'll ever hear from them again. But for 72 seconds on August 15th, 1977, something remarkable happened. A telescope in Ohio detected a signal from space that we still can't explain. It might have been natural, some rare astronomical phenomenon we don't understand, or it might have been artificial. A message from another civilization. We're not sure, but the possibility is enough. Enough to keep searching, enough to keep wondering, enough to keep hoping that one day we'll hear it again, or hear something else, something that tells us we're not alone, and that's where we are. 46 years later, still searching, still listening. The WOW signal remains unexplained. A mystery, a puzzle, a source of endless speculation and debate. It's been analyzed and reanalyzed. Every proposed explanation has been examined. None have satisfied everyone. The signal stands as one of the great anomalies in the history of astronomy. Right up there with fast radio bursts before we understood them, with pulsars before we identified them, with quasars before we figured out what they were. The difference is, those other mysteries got solved. The wow signal hasn't. Not yet. Maybe it never will. Or maybe tomorrow, someone will point a telescope at the right patch of sky at the right time and hear it again. And this time, we'll be ready. We'll record it. We'll analyze it. We'll confirm it. And then, finally, we'll know. Until then, we wait. We listen. We wonder. The search continues. Let's talk about what makes a signal interesting and from a SETI perspective, because this helps us understand why the WOW signal stands out even among other anomalies. There are a few key characteristics researchers look for. First, the signal should be narrowband. Natural sources like stars and galaxies emit across broad ranges of frequencies. Their energy is spread out. Artificial transmitters, like the ones we build, concentrate energy into narrow frequency bands. That's more efficient. You get a stronger signal for less power, so a narrow band signal suggests technology. The WOW signal was very narrow band, less than 10 kilohertz wide. That's characteristic of an artificial transmitter. Not proof, but suggestive. Second, the signal should be at a meaningful frequency. The hydrogen line at 1420 MHz is meaningful. Every civilization that studies radio astronomy knows about it. It's a natural beacon frequency. There are other meaningful frequencies too, like 21 centimeters, the wavelength of the hydrogen line, or multiples and harmonics of fundamental frequencies. Signals at random frequencies are less interesting. They could be anything, but a signal at a significant frequency suggests intent. Someone chose that frequency deliberately. The WOW signal was right near the hydrogen line. Again, not proof, but suggestive. Third, the signal should come from a plausible location. A signal from nearby space is less interesting. It's probably human-made. Satellites, space debris, Interference, a signal from deep space from the direction of stars or galaxies, is more interesting. The WOW signal came from the constellation Sagittarius, from a region of sky containing many stars, roughly 78 light-years away based on the estimated direction. That's deep space, not local, not a satellite or aircraft, a plausible source for an extraterrestrial signal. Fourth, the signal should have characteristics that rule out obvious natural explanations: duration, intensity, modulation. The WOW signal's 72-second duration matched perfectly with a point source drifting through Big Ear's beam. The intensity was high, 30 times background. The modulation was absent, just a carrier wave. All of this fits artificial transmission. It doesn't fit known natural phenomena well. Fifth, ideally the signal should repeat. This is the big one. Repeatability allows verification. If a signal appears once and never again, you can't study it. You can't confirm it's real or determine its nature. But if it repeats, you can point multiple telescopes at it, record it with different instruments, analyze it thoroughly, build certainty. The WOW signal failed this criterion. It appeared once, never again. This is why we can't say definitively what it was. We have one data point. That's not enough. But everything else about the signal was compelling. That's why it remains interesting. It checked almost every box except the most important one. There's an interesting parallel between the WOW signal and how we've thought about life in the universe over time. For most of human history, we assumed we were alone. Earth was special, unique, created specifically for us. Other planets, if they existed, were barren, lifeless. This view slowly changed. Copernicus showed Earth wasn't the center of the universe. The Sun was just one star among many. Other stars probably had planets. As telescopes improved, we confirmed this. Planets are common. Most stars have them. Then we started asking, could those planets host life? Are conditions right? We learned that the ingredients for life are common: water, organic molecules, energy, all abundant in the universe. So maybe life is common too. We haven't found it yet beyond Earth, but the odds seem good. Intelligence is the next step. If life is common, maybe intelligence evolves often. Maybe technological civilizations arise regularly. The universe might be teeming with them, or maybe not. Maybe intelligence is rare, a fluke. We don't know. The WOW signal, if it was artificial, would tell us intelligence exists elsewhere. That it has arisen at least twice, once here, once there. That's profound. It means the universe isn't just full of life, it's full of minds, thinking, communicating, technological minds. And if it happened twice, it probably happened many times. The implications cascade, from alone to one among many, from unique to typical, from special to ordinary. This is why the signal matters so much. It's not just about detecting radio waves. It's about understanding our place in the cosmos. The search for the WOW signal, and signals like it, also reflects human optimism. Despite decades of silence, despite thousands of observations yielding nothing, we keep looking. We keep hoping. This speaks to something deep in our nature. We're curious. We want to believe we're not alone. We want to find friends in the stars, even if the odds are long. Even if success seems unlikely, we persist. This optimism is beautiful. It's also scientifically justified. The universe is vast. The number of stars is enormous. The number of planets is staggering. Life might be rare, but given enough opportunities, rare things happen. Intelligence might be a 1 in a billion shot, but there are billions of chances. Somewhere, someone might be out there, and if they are, we owe it to ourselves to try to find them. There's also a practical benefit to SETI research that's often overlooked. The technology developed for searching for alien signals has applications elsewhere. Better receivers, more efficient signal processing, advanced algorithms for detecting patterns in noise. These technologies help with other forms of radio astronomy. They help with communications technology. They advance our understanding of the electromagnetic spectrum and how to use it. SETI might not find aliens, but the effort pushes science forward regardless. The search justifies itself through the knowledge gained, even if the ultimate goal remains elusive. In the end, the wow signal is a story about mystery, about a brief moment when something extraordinary might have happened, about one astronomer seeing something on a printout that no one had seen before or has seen since, about a signal from space that defies explanation. We've analyzed it, we've searched for it, we've debated it, and we still don't know what it was. That uncertainty is uncomfortable, but it's also exciting. It means there are still mysteries, still unknown things. The universe hasn't revealed all its secrets. There's still room for discovery, still room for wonder. And that's what keeps us searching. Not certainty, not guarantees, but possibility. The possibility that out there, in the darkness, someone's broadcasting. And maybe, if we listen long enough, we'll hear them. The silence following the wow signal raises one of the most perplexing questions in all of SETI research. Why haven't we heard it again? If the signal was artificial, if some civilization deliberately transmitted it, why only once? There are several possible explanations, and each one tells a different story about what might be happening out there in the cosmos. The first possibility is that the signal was part of a rotating broadcast. Imagine a lighthouse. It sweeps its beam in a circle. If you're standing in one spot, you see the light briefly as the beam passes you. Then, darkness until the beam comes around again. The time between flashes depends on how fast the lighthouse rotates. If an alien civilization is doing something similar, broadcasting a beam that sweeps across the galaxy, we might only catch it when the beam points at us. The WOW signal could have been one sweep. The beam pointed at Earth for 72 seconds. Then it moved on to target other star systems. When will it point at us again? That depends on how long the full rotation takes. Days, months, years, centuries? If it's a long rotation period and we haven't been observing continuously, we might have missed subsequent passes. Or the next pass might not happen for decades. We'd have to be watching at exactly the right time to catch it again. The second possibility is that the transmission was brief and directional. Maybe they weren't sweeping. Maybe they pointed directly at our solar system, transmitted for a short time, then stopped. Why would they do that? Perhaps they're systematically surveying the galaxy. They have a list of star systems with potentially habitable planets. They send a ping to each one, a brief hello. If anyone's listening, they'll respond. Once they've sent their message to one system, they move on to the next. They're not going to keep broadcasting at us forever. They sent their message. They're waiting for a response. Meanwhile, they're sending messages to other stars. This makes sense from an efficiency standpoint. Why waste energy transmitting continuously at one target? Send your message once. Wait for a reply. If you get one, great. Establish communication. If not, maybe try again later or move on. From their perspective, they did their part. They sent a signal. If we were paying attention and wanted to respond, we could. The fact that we didn't might tell them we're not here or not interested or not technologically advanced enough. The third possibility is that the signal was a one-time event, not part of a regular broadcast, not part of a systematic survey, just a singular transmission. Maybe it was a test. They were checking if their transmitter worked. They fired it up, sent a test signal, verified it was functioning, then shut it down. We happened to catch that test. Or maybe it was an accident, a malfunction, a power surge. Their equipment did something it wasn't supposed to do. It broadcast briefly, then shut down, or was shut down. Or maybe it was a ceremonial transmission, some significant event, a planetary holiday, a historical anniversary. They broadcast a special message to the universe once, then back to normal life. Any of these scenarios could explain a one-time signal. The fourth possibility, and this is darker, is that they're no longer there. The signal was sent 78 years ago. It took that long to reach us at light speed. 78 years isn't much on cosmic scales, but it's enough time for a civilization to collapse. War, environmental disaster, asteroid impact, plague, internal societal breakdown. Any number of catastrophes could have ended them. They existed in 1999. They were broadcasting, but by 2024, they might be gone. This is the Great Filter Hypothesis at work. The idea that there's some challenge or series of challenges that civilizations face. Most don't survive. If intelligent life is common, but long-lived civilizations are rare, the galaxy might be full of brief sparks of technology. Civilizations that arise, flourish for a few centuries or millennia, then vanish. We might be detecting their last gasps, signals sent by civilizations that no longer exist by the time we receive them. It's a sobering thought, but it's possible. The fifth possibility is that we're not listening right. Maybe they transmitted again, but we missed it. Big Ear was demolished in 1998. Other telescopes have searched, but they're different. Different sensitivities, different frequency coverage, different sky coverage. If the signal repeated, but at a slightly different frequency, or from a slightly different location, or when no one was observing, we'd miss it. SETI observations are sparse. We can't monitor every direction, every frequency, all the time. We sample. We observe a region for a while, then move on. If the signal happens when we're not looking, it goes undetected. This is frustrating, but it's the reality of limited resources. We're doing our best with what we have, but we might be missing things. The sixth possibility, and this is the skeptical view, is that the signal wasn't artificial to begin with. It was some natural phenomenon we don't understand, a rare event. Something that happens occasionally under specific conditions. Maybe an interaction between cosmic rays and the interstellar medium. Maybe emission from an unusual type of star or stellar remnant. Maybe something involving the solar system's magnetic field or atmosphere. We don't know. But natural explanations are always more likely than artificial ones. Extraordinary claims require extraordinary evidence. One signal isn't extraordinary enough. It's interesting. It's compelling. But without repetition or additional data, we can't rule out natural causes. Maybe someday we'll figure out what natural process could create a signal like that. Then the mystery will be solved. It won't be aliens, just nature being weird. Each of these possibilities is plausible. We can't distinguish between them with the data we have. That's the frustration. The wow-ow signal gives us just enough information to speculate, but not enough to conclude. We're left guessing, imagining scenarios, building stories around a single data point. This is why repeatability is so important in science. One observation is an anecdote. Multiple observations are data. With data, you can test hypotheses. You can build theories. With an anecdote, you can only wonder. Let's talk about other signals that have captured attention over the years, because understanding how they were resolved helps put the WOW signal in context. In 2020, the Parkes telescope detected BLC-1, Breakthrough Listen Candidate 1. It was narrowband. It appeared to come from Proxima Centauri. It shifted in frequency over time in a way consistent with motion. All signs pointed to something interesting. Excitement built. Could this be it? Could we have finally detected a signal from our nearest stellar neighbor? The media picked it up. Headlines declared we might have found aliens. But then further analysis revealed the truth. The signal was terrestrial. It came from Earth. Specifically, it matched the pattern of interference from electronic equipment. The frequency drift was due to temperature changes in some device. As it heated or cooled, its oscillator frequency changed. That's what caused the drift that initially looked like motion. BLC-1 was a false alarm. Disappointing but educational. It showed how careful you have to be, how easy it is to mistake human-made signals for extraterrestrial ones. Fast radio bursts initially sparked speculation too. These are intense pulses of radio energy lasting milliseconds. They're incredibly powerful. The energy released in a few milliseconds equals what the sun emits in days. When they were first discovered, astronomers were puzzled. What could produce such intense, brief bursts? Some speculated about alien megastructures, energy beams from starship propulsion systems, signals from advanced technology. But as more FRBs were detected and studied, a natural explanation emerged. They come from highly magnetized neutron stars. When their magnetic fields undergo sudden reconfiguration, they release enormous amounts of energy in a brief burst. That's what we're seeing. FRBs are natural, not artificial. This is the pattern. Something anomalous is detected. Speculation ensues. More data is gathered. Natural explanation found. Mystery solved. The difference with the wow-ow signal is we can't gather more data. We caught it once. It didn't repeat. We're stuck with that single observation. So the mystery remains unsolved. Not because we haven't tried to solve it, but because we don't have enough information. This makes the Weibo signal unique among astronomical anomalies. Most get explained eventually. This one hasn't. And unless it repeats or we develop new theoretical understanding of what could cause such a signal naturally, it might never be explained. It will remain an asterisk in the history of astronomy. An interesting footnote: the signal that might have been aliens, but we'll never know for sure. Jerry Amon's role in this story is central, and his perspective is worth exploring more deeply. He was a professor at Franklin University in Ohio. He volunteered his time to help with SETI research. He wasn't a famous astronomer. He wasn't seeking glory or recognition. He was just a curious person who wanted to contribute to something meaningful, searching for extraterrestrial intelligence. That's how he ended up sitting at home reviewing computer printouts from Big Ear. Mundane work, page after page of numbers and letters representing radio signals from space. Mostly noise, mostly boring, but important. Someone had to check the data. Someone had to look for anything unusual. Amon did that job. When he saw the 6EQUJ5 sequence, his immediate reaction was human and authentic, not a calculated scientific response. Just wow. He recognized instantly that this was different. This stood out, and he marked it. That red pen circle became iconic. It's been reproduced in articles and documentaries. It's a symbol of the moment when a human being saw something that might have been contact with another intelligence. Amon didn't claim it was aliens. He was cautious. He knew it could be many things, but he also knew it was worth investigating, worth getting excited about. His reaction was balanced, recognition of significance without overreach. That's scientific integrity. In the years after the discovery, Amon gave talks about the signal. He participated in discussions and debates. He reviewed every proposed explanation. When the comet hypothesis was published in 2017, he examined it critically. He pointed out its flaws. He said he remained open to natural explanations, but this one didn't fit the data well. He maintained that position of informed uncertainty. I don't know what it was. It might have been artificial. It might have been natural. The data doesn't let us conclude definitively. That honesty is rare. In an era of hype and overstatement, Amon resisted the temptation to claim more than the evidence supported. He didn't write books proclaiming he'd found aliens. He didn't become a media personality. He just remained a thoughtful scientist who saw something interesting and wanted to understand it. Amon passed away in 2020 at age 82. He lived with the mystery his entire life. From 33 years old, when he discovered the signal to his death 43 years later, he never got an answer. The signal remained unexplained, but his legacy is secure. He's the person who found the most compelling candidate for extraterrestrial communication we've ever detected. His name is forever linked to the WOW signal, and his approach, careful, critical, curious, sets an example for how to handle anomalous data. Don't dismiss it. Don't overstate it. Investigate it. Share it. Let others examine it. Remain open to evidence. That's the scientific method. Amon embodied it. So why do we keep searching despite decades of silence? Why dedicate resources and careers to a quest that hasn't succeeded? There are several reasons. The first is the potential payoff. Detecting extraterrestrial intelligence would be the most important discovery in human history. It would answer fundamental questions about life, intelligence, and our place in the universe. It would transform philosophy, religion, science, culture. Everything would change. Even a small chance of success justifies the effort because the reward is so enormous. If there's 1% chance, or 1/10 of 1% chance, or 1,000th of 1% chance, it's still worth trying. The possible gain outweighs the cost. The second reason is scientific value. Even if we don't find aliens, SETI research advances our knowledge. We learn about the universe, about radio astronomy, about signal processing, about the conditions necessary for life and intelligence. Every observation adds to our understanding. Every null result narrows the parameter space. If we search thoroughly and find nothing, that tells us something important. It suggests intelligence is rare. Perhaps we're among the first. Perhaps there's a great filter we've passed that others haven't. Perhaps technology doesn't last long enough for civilizations to overlap in time and space. These conclusions have value. They inform our thinking about the future of humanity and our responsibilities as a potentially rare intelligence. The third reason is human nature. We're curious. We wonder. We want to know if we're alone. This drive to explore and understand is fundamental to who we are as a species. It's why we climbed mountains, crossed oceans, explored continents, went to the moon, sent probes to the outer planets and beyond. We want to see what's out there. We want to push boundaries. Searching for extraterrestrial intelligence is an extension of this. It's exploration. It's the frontier. And frontiers attract people who can't resist the call, who need to know, who have to try. SETI attracts these people. They're willing to dedicate their lives to a long shot because the possibility, however remote, is compelling. The fourth reason is hope. Hope that we're not alone, that somewhere out there, someone else looks at the stars and wonders the same things we wonder. Someone else builds telescopes and listens. Someone else has art and music and science and dreams. The universe is vast and ancient. It would be a terrible waste if we're the only ones experiencing it, the only minds capable of understanding it. SETI is motivated by hope that the universe is richer than that, more interesting, more alive. This hope sustains researchers through years of negative results. It keeps them going because maybe tomorrow is the day. Maybe the next observation catches something. You have to keep trying. You have to keep listening. Modern SETI efforts are more sophisticated than anything available when the wow signal was detected. Breakthrough. Listen, launched in 2015, is the most comprehensive search ever undertaken. It's using some of the world's most powerful telescopes. The Green Bank Telescope in West Virginia, the Parkes Telescope in Australia, the Meerkat Array in South Africa. These instruments can detect signals far fainter than Big Ear could. They cover more frequencies. They observe more targets. The project is scanning millions of stars and thousands of galaxies, recording vast amounts of data, and applying machine learning algorithms to analyze it. The goal is to catch anything unusual, any signal that doesn't fit natural patterns. So far, no confirmed detections, but the search continues. Breakthrough Listen is also publicly releasing its data. Anyone can download it, analyze it, look for patterns the algorithms might have missed. Citizen scientists around the world are participating. This crowdsourcing approach increases the chances of finding something. More eyes on the data, more perspectives, more opportunities for insight. It's a democratization of SETI, not just professionals. Everyone can contribute. This feels right. The question of whether we're alone belongs to all of humanity, not just scientists. Everyone has a stake in the answer. There are also new approaches being tried. Optical SETI looks for laser pulses from space. The idea is that advanced civilizations might use lasers to communicate. Laser light can be very powerful and directed. A strong laser aimed at us would briefly outshine a star. We'd see a flash. If we're watching at the right moment, optical SETI scans the sky looking for these flashes. It's harder than radio SETI because optical detectors are less sensitive and the field of view is smaller. But it's another avenue, another way to search. The more ways we look, the better our chances. Some researchers are also thinking about what kind of signals we should look for beyond simple carrier waves. Maybe advanced civilizations encode information in complex ways. Modulation schemes, spread spectrum techniques, error correction codes. Things we might not recognize as artificial unless we know what to look for. This requires thinking about how we would communicate if we were trying to send a message to the stars. What would we include? How would we structure it? Then looking for those patterns. It's a challenging problem. You're trying to imagine alien minds and what they might do, but it's worth considering. Maybe we've been looking for the wrong kind of signal. Another idea is looking for techno-signatures, not direct communications, but evidence of technology. Energy signatures from megastructures, industrial pollution in exoplanet atmospheres, waste heat from massive computing systems. If civilizations exist, they use energy. They modify their environment. They leave traces. Maybe we can detect those traces before we detect deliberate signals. Techno-signature searches are relatively new, but they're gaining traction. They broaden the scope of SETI beyond listening for radio waves. They make SETI part of general astronomy. Every observation of an exoplanet, every study of an unusual star, it might reveal evidence of intelligence. What if we never hear the wow-wow signal again? What if we search for another 40 years, another century and find nothing? What then? Do we give up? Do we conclude we're alone? Or do we keep searching? The answer depends on your philosophy. Some would say silence is an answer. If we search thoroughly and find nothing, the universe is telling us something. Intelligence is rare, maybe unique. We should accept that and move on, focus our efforts elsewhere. Others would say silence proves nothing. The universe is too big, the timescales too vast. Civilizations might be common, but spread so far apart in space and time that contact is essentially impossible. We could search forever and never find anyone, even if they exist. So, we keep searching, not because we expect success, but because the question matters. Because giving up means accepting we'll never know. There's wisdom in both views. The universe doesn't owe us answers. We might never know if we're alone. That uncertainty might be permanent, part of the human condition, something we have to live with. The wow signal embodies this uncertainty. It's a maybe, a possibly, a tantalizing hint that's not enough to confirm anything, and maybe that's all we'll ever have, a collection of maybes, signals that might have been artificial, observations that might indicate intelligence, but never quite enough to be sure. We have to be okay with that. We have to keep searching anyway, because the alternative, not searching, is worse. If we don't look, we guarantee we'll never find anything. If we do look, we might. That slim possibility is enough. The bigger picture here is about humanity's relationship with the cosmos. We're a young species. We've existed for a few 100,000 years. We've had technology for barely a century. We're just beginning to explore space, just beginning to ask these questions. In cosmic terms, we're infants. We're taking our first steps, our first attempts to reach out. The wow signal, if it was artificial, might have been someone else's attempt to reach out. Two infants in a dark room. One cried out, the other heard. But they can't find each other. They don't know how. They're scared, alone, hoping. That's where we are, crying out, listening, hoping someone hears us, hoping we hear them, not knowing if anyone's there. This search also connects to deeper questions about consciousness and intelligence. What does it mean to be aware? To think? To understand? Are we special because we have these abilities, or are they common in the universe? If we find others, what will they be like? Will they think like us? Have similar values? Similar curiosity? Or will they be fundamentally alien, so different we can't understand each other? These questions matter. They affect how we see ourselves, our intelligence, our consciousness, our place. If we're alone, these traits are precious, unique. We carry a special responsibility to preserve them. If we're not alone, we're part of a larger community, a cosmic civilization. We have neighbors, peers, potential friends or rivals. Either answer changes everything. The wow signal reminds us that the universe might be stranger and more wonderful than we imagine. That on one night in 1977, something happened. Something we still don't understand. A signal from space that fits no easy explanation. Maybe it was aliens. Maybe it was nature doing something weird. We don't know. But the fact that it happened, the fact that we detected it, the fact that we're still talking about it nearly 50 years later, that tells us something. It tells us the universe still has mysteries, still has surprises, still has things we haven't figured out. And that's beautiful, that's exciting, that's worth exploring. So we keep listening, keep searching, keep hoping. The telescopes scan the sky. The algorithms process the data. The researchers analyze the results. Night after night, year after year. Most of the time they find nothing, just noise, just the universe humming to itself. But occasionally something stands out, something anomalous, something worth investigating. And every time that happens, there's a moment, a brief moment when you think, maybe this is it. Maybe this is contact. Maybe we're not alone. That moment is what drives SETI, that possibility, that hope, wonder. The wow signal captured that moment for Jerry Amon, for everyone who's learned about it since, for all of us who look at those 6 characters, 6EQUJ5, and imagine what they might mean. They might mean nothing, a cosmic coincidence, a glitch, a natural phenomenon, or they might mean everything, a message, a greeting, proof that we're not alone. We don't know. We may never know. But we'll keep wondering, keep searching, keep hoping, because that's what we do. That's who we are. A species that looks at the stars and asks, is anyone out there? And listens, and waits, and dreams. Let's explore the technical challenges of verifying signals like the WOW more deeply, because this reveals just how difficult SETI is. When a radio telescope detects something unusual, the first question is always, is this real or is it interference? Earth is saturated with radio signals. We use radio for everything: communications, navigation, remote sensing, entertainment. Every cell phone tower broadcasts. Every satellite transmits. Every radar installation sends out pulses. All of this creates an electromagnetic fog, a background of human-made signals that radio telescopes have to filter through. Most SETI observations are contaminated by terrestrial interference. You detect something, you get excited. Then you realize it's a satellite passing overhead, or a plane with active radar, or someone's illegal transmission bleeding into a protected frequency. False alarms are constant. Frustrating, time-consuming. The WOW signal passed initial interference checks. It was at a protected frequency. It came from a fixed point in space. It had the right duration. But without repetition, you can never be completely certain. Maybe it was a one-time glitch, a piece of equipment malfunctioning in just the right way to mimic a distant source. Maybe it was a reflected signal bouncing off something in an unusual way. Maybe it was atmospheric, some weird ionospheric effect that channeled a terrestrial transmission to appear to come from space. These are all unlikely. The more you check, the more the signal looks genuine. But you can't rule out terrestrial interference completely without catching it again and verifying it with multiple independent telescopes simultaneously. That's the gold standard. Multiple detections, multiple instruments, all seeing the same thing at the same time. Then you know it's real. The WOW signal doesn't meet that standard. It's a single detection, one instrument, one moment, compelling but not conclusive. There's also the question of what information a signal might contain. The WOW signal was just a carrier wave, a spike at one frequency, no modulation that we could detect, no pattern, no data encoded in it. If aliens wanted to communicate, wouldn't they include a message? Wouldn't they encode information somehow? Maybe. Or maybe the carrier wave itself is the message. The message is, we're here, we have technology, we can build transmitters. We're broadcasting at a frequency you'd notice. That's enough for first contact. The detailed messages can come later. First, you establish that communication is possible. You get each other's attention. Then you figure out protocols, how to encode information, what language to use, what topics to discuss. The carrier wave is the handshake, the hello, not the conversation. But this raises another challenge. If we receive a modulated signal with information encoded in it, Can we decode it? This is the problem of interstellar communication. Two civilizations with no common language, no shared references, no mutual history. How do you communicate? Mathematicians and linguists have thought about this. The consensus is that math and science provide a foundation. Mathematical constants, like pi. Physical constants, like the speed of light. These are universal. Any technological civilization knows them. You can use them as a starting point. Build a vocabulary, define terms, gradually construct a language. It's slow, but possible in principle. Whether it's practical is another question. The conversation proceeds at light speed. Messages take years or decades or centuries to cross the distance between stars. You send a message. Years later, you get a reply. Years after that, your response arrives. It's an agonizingly slow exchange, and both civilizations have to maintain continuity, keep the project funded, keep the knowledge preserved across generations. Don't go extinct before the conversation concludes. These are serious challenges. Some researchers have proposed active SETI. Instead of just listening, we send messages. Powerful transmissions aimed at nearby stars. We announce ourselves. We say, we're here, we're intelligent, we want to talk. This is controversial. Some argue it's dangerous. We don't know what's out there. Maybe there are hostile civilizations. Maybe broadcasting our location is stupid. Maybe the galaxy is a dark forest where everyone hides because being found means being destroyed. This is speculative but concerning. Others argue we're already visible. Our radio and TV broadcasts have been leaking into space for a century. Anyone within 100 light years with good enough equipment could detect us. So, we're not exactly hiding. Broadcasting more wouldn't change much. We're already exposed. Might as well try to initiate conversation. The debate about active SETI touches on deeper issues about risk and benefit. What's the upside of contact? Learning from another civilization, gaining knowledge, technology, perspective, friendship, cultural exchange. These are enormous benefits. What's the downside? Possible hostility, exploitation, invasion, cultural contamination, loss of autonomy. These are serious risks. How do you weigh them? Is a 1% chance of catastrophe worth a 99% chance of benefit? What about 10%, 50%? We don't know the probabilities, we're guessing. Operating in profound uncertainty. Different people reach different conclusions. Some are optimistic, others are cautious. There's no consensus. The wow signal, if it was artificial, represents passive SETI. Someone else broadcast. We listened. We caught it. This seems safer than active SETI. We're not revealing ourselves. We're just eavesdropping. But even this has implications. If we confirm the signal was artificial, what do? Do we announce it to the world? Do we keep it secret? Do we respond? International protocols exist for this scenario. If SETI detects a confirmed extraterrestrial signal, researchers are supposed to verify it thoroughly, inform other observatories, confirm it independently, then announce it publicly. No government or institution should control the information. It belongs to humanity. Everyone should know. But then what? Do we send a reply? Who decides what to say? Who speaks for Earth? These are political questions, not scientific, and they're unresolved. We don't have good answers. We're hoping the problem doesn't come up, but if it does, we'll have to figure it out. Let's talk about the psychology of SETI researchers because their motivation and mindset are interesting. These are people who dedicate their careers to a quest that probably won't succeed in their lifetimes. They know the odds are long. They know funding is scarce. They know their work is often dismissed as fringe science. But they persist. Why? Some are driven by curiosity. They have to know. The question of whether we're alone obsesses them. They can't let it go. They're compelled to search even if they never find anything. Others are motivated by hope. They believe contact would be transformative, would benefit humanity. They want to be part of making that happen. They're willing to spend their lives on the attempt, even if it's futile. Still, others see SETI as scientifically justified, regardless of outcome. The search itself is valuable. It advances technology and knowledge. Success would be wonderful, but failure isn't wasted effort. There's also a romantic element. SETI researchers are modern explorers. They're sailing into unknown seas, searching for new worlds, new civilizations. This has always attracted certain personalities, people who can't be satisfied with the known, who need the frontier, who have to push boundaries. SETI offers that, an endless frontier, an unlimited horizon. You can search forever and never run out of places to look, never exhaust the possibilities. There's always another star, another frequency, another observation. For people with explorer temperaments, this is irresistible. They're not necessarily expecting to find anything. They're enjoying the journey. The search itself is the reward. Understanding this psychology helps explain why SETI continues despite lack of success. It's not just stubbornness or delusion. It's a combination of scientific value, personal motivation, and philosophical conviction. These people believe the question matters, whether we're alone, whether intelligence is common or rare, whether the universe is full of life or barren. These questions are profound, worth pursuing. Even if answers are elusive, even if we search for centuries and never find anything, the attempt is meaningful. It reflects who we are as a species. Curious, hopeful, determined. It's one of the better aspects of human nature, the drive to explore, to seek, to wonder. The future of SETI looks promising in terms of technology, new telescopes coming online, better detectors, more powerful computers, faster algorithms. We're developing tools that would have seemed like science fiction 50 years ago. The square-kilometer array, when completed, will be orders of magnitude more sensitive than anything we've had before. It will be able to detect signals from across the galaxy that previous telescopes couldn't. It will scan vast areas of sky simultaneously. It will operate continuously. If there are signals to find, SCAR has a good chance of finding them. Similarly, advances in optical telescopes and infrared astronomy open new search strategies. We're not just looking for radio signals anymore. We're looking for laser pulses, waste heat, spectral signatures, anything that might indicate technology. We're casting the net wider, covering more possibilities. artificial intelligence is also transforming SETI. Machine learning algorithms can analyze data faster and more thoroughly than humans. They can identify patterns we'd miss, flag anomalies for investigation, handle the flood of data from modern telescopes. Without AI, much of the data would go unexamined. There's simply too much. But with AI, we can process everything, look at every observation, check every frequency. The only limit is computing power, and that keeps improving. What took weeks of human effort in the 70s takes seconds for modern algorithms. This acceleration is significant. We're searching more thoroughly, efficiently than ever before. But technology alone isn't enough. We also need persistence, patience, long-term commitment. SETI is a marathon, not a sprint. It might take decades or centuries to succeed, or it might never succeed. We have to be okay with that. We have to search anyway, because not searching guarantees failure. Only by looking do we have any chance of finding. This requires institutions and funding that can sustain efforts over long timescales. Private philanthropy helps. Breakthrough. Listen is funded by Yuri Milner's fortune. That provides stability for a decade or more. But what about century-long searches? Who funds those? How do we maintain continuity across generations? These are practical challenges that need solving. SETI can't rely on short-term grants. It needs endowments, permanent infrastructure, commitment. That's harder to achieve than developing new technologies. There's also the question of what happens if we do find something, if we detect a confirmed signal, if we establish that it's artificial. That moment would be historic, transformative, but also chaotic. The media would explode, governments would scramble, religious institutions would respond, everyone would have opinions, everyone would want to be involved. Managing that would be difficult. The scientific community would need to stay calm, focus on verification, on gathering more data, on understanding what we've found. But there would be pressure, demands for immediate answers, speculation running wild, conspiracy theories, panic, celebration, all at once. It would be overwhelming. International coordination would be crucial. No single nation should control information about extraterrestrial contact. It's a global matter, affects everyone. The United Nations has protocols for this. The Committee on the Peaceful Uses of Outer Space has working groups on near-Earth objects and space debris. They'd likely take the lead on coordinating response to a SETI detection, but their authority is limited. Nations can ignore UN recommendations. There's no enforcement mechanism, so coordination would require voluntary cooperation. Shared interest in managing the situation responsibly. Whether that would happen is uncertain. National interests might override global cooperation, especially if contact offers potential technological or strategic advantages. This could get messy fast. For now, these scenarios are hypothetical. We haven't detected anything confirmed. The WOW signal remains unexplained. Intriguing, but not definitive. We're still searching, still listening, still hoping. The telescopes scan the sky, night after night, season after season, year after year. Most of the time, they find nothing, just the background noise of the universe, stars and galaxies doing their thing, natural processes humming along. But occasionally something stands out, a candidate signal, an anomaly, and for a brief moment, excitement builds. Could this be it? Could this be the one? Then further analysis reveals the truth. Interference, natural phenomenon, false alarm, back to searching. This cycle repeats endlessly. Detect, investigate, dismiss, repeat. It's tedious, frustrating, requires enormous patience, but you keep going because maybe next time, maybe the next signal is real. The wow-ow signal stands out precisely because it hasn't been explained away. 46 years later, we're still talking about it, still debating what it might have been. That longevity is remarkable. Most anomalies get resolved quickly, within days or weeks or months. The wow-ow signal has resisted resolution for decades. This suggests it was genuinely unusual, not a simple case of interference or misidentification, something rare, something that doesn't fit our understanding. Whether that something was natural or artificial, we don't know. But its persistence as an unsolved mystery keeps it alive in the collective imagination. It's become iconic, a symbol of the SETI quest, a reminder that the universe might surprise us. Jerry Amon's red ink wow has become an indelible part of science history. That spontaneous reaction, that moment of recognition, it captures something essential about discovery. The human element, the excitement, the wonder. Science is often portrayed as cold, detached, purely rational. But scientists are human. They feel excitement. They experience wonder. They have emotional reactions to discoveries. Amon's wow embodies that. It's raw, authentic, unfiltered, and it reminds us that behind every scientific finding is a person. Someone who noticed something, someone who cared enough to investigate, someone whose life was touched by the discovery. That's worth remembering. Science is a human endeavor, driven by human curiosity and emotion, not just logic and equations. There's another dimension to the WOW signal worth examining, the cultural impact it's had beyond just the scientific community. The signal has appeared in books, documentaries, television shows, movies. It's become part of popular culture, a touchstone for discussions about aliens and first contact. When people talk about whether we've ever received messages from space, the wow-ow signal comes up. It's the best example we have, the most compelling case. This cultural resonance matters. It keeps the question alive in public consciousness. It reminds people that SETI is real, that we're actually searching, that maybe someday we'll find something. This public awareness can translate into support, into funding, into young people choosing careers in astronomy and SETI. Cultural impact has practical consequences. The signal has also inspired art. Musicians have composed pieces based on it. Visual artists have created works exploring themes of contact and cosmic loneliness. Writers have used it as a launching point for stories about first contact. This artistic response is fascinating. It shows how a scientific anomaly can resonate emotionally. The wow-ow signal isn't just data. It's a narrative, a mystery story, a thriller with no resolution. Artists respond to that. They explore the emotional landscape, What does it mean to hear a message and lose it? What does that say about our place in the universe, about connection and isolation? These are themes artists can work with, and their explorations enrich our understanding of the signal's significance beyond just the technical details. Philosophically, the wow signal raises questions about evidence and belief. How much evidence do you need before you accept something extraordinary? If you're a skeptic, one signal isn't enough. You'd want repetition, independent confirmation, multiple lines of evidence, all pointing to the same conclusion. Only then would you accept that it was artificial. This is a reasonable position. Extraordinary claims require extraordinary evidence. But if you're more open-minded, one signal might be suggestive enough. Not proof, but compelling. Enough to lean toward the artificial hypothesis while acknowledging uncertainty. This is also reasonable. Different people weigh evidence differently, have different thresholds for belief. The wow signal sits in this middle ground where smart, informed people can disagree about what it means. This relates to a broader epistemological question. How do we know what we know? What counts as knowledge versus speculation? In science, knowledge comes from repeatable observations and testable theories. One-off events are problematic. They can't be repeated. They can't be tested, so they don't easily fit into the scientific framework. But they might still be real. They might still be important. How do we handle them? The wow signal is an example of this challenge. We have data. We know something happened, but we can't reproduce it. We can't test it. So what do we do with it? We document it. We preserve it. We keep it in the back of our minds as we continue searching. And we hope that someday more data emerges that helps us understand it. That's the best we can do. The signal also prompts reflection on what we mean by contact. If the wow signal was artificial, was that contact? We received something, but there was no exchange, no conversation, no mutual awareness. They sent, we received. But they don't know we received. We can't respond. We don't know where they are precisely enough to aim a message back. So is that contact? Or is it just eavesdropping? Detection without connection? This semantic question matters for how we think about first contact. Many people imagine it as a dialogue, messages back and forth, but it might not be. It might be asymmetric, one-sided. We hear them, but they don't hear us, or vice versa. That's still significant, still meaningful. But it's different from the mutual contact scenario most people envision. The timeline of SETI since the wow signal is instructive. 1977 to 2024 is 47 years. In that time, technology has improved dramatically. Computers are millions of times more powerful. Telescopes are more sensitive. Algorithms are more sophisticated. We've discovered thousands of exoplanets. We've learned that rocky planets in habitable zones are common. The universe seems more hospitable to life than we thought in the 70s. All of this should have improved our chances of detection, and yet we haven't found anything confirmed. No second wow signal, no other compelling candidate, just silence. This tells us something. Either intelligence is very rare, or it's not broadcasting, or we're not looking right, or the distances and timescales are so vast that even common civilizations rarely overlap. Each possibility has implications. The Great Silence, as it's called, is one of the most profound mysteries in science. Why don't we see or hear evidence of extraterrestrial intelligence? The Fermi paradox. If civilizations are common, where is everyone? Many answers have been proposed. Maybe civilizations don't last long. They destroy themselves. Nuclear war, environmental collapse, AI gone wrong. Whatever the cause, technological civilizations might be unstable, prone to self-destruction within a few centuries of developing radio. If that's common, we'd see few signals, just brief sparks before darkness. Maybe civilizations transcend. They develop beyond the need for radio. They use quantum entanglement or some technology we haven't imagined. They're still out there, but we can't detect them with our primitive tools. Maybe they're deliberately quiet, hiding. The dark forest hypothesis. Broadcasting is dangerous, so everyone stays silent. Maybe they're not interested in contact. They know we exist but don't care. We're not worth their time. Like ants by the roadside, visible but irrelevant. Maybe we're early. The universe is 13.8 billion years old, but perhaps Earth is among the first planets to develop technological life. We're pioneers. First to ask the question, not yet the second. Each of these explanations has strengths and weaknesses. None can be ruled out. The wow-wow signal, if artificial, argues against some but not all. If civilizations broadcast, the Great Silence is less profound. Someone was transmitting. We heard them, but only once. So maybe transmissions are rare, brief, infrequent, not the continuous, loud, obvious signals some expected. This shifts our search strategy. We need to be luckier, or more patient, or more comprehensive in our coverage. We can't just target a few hundred stars and call it done. We need to survey millions, billions, cover the whole sky, monitor continuously, be ready for transient signals. This is more demanding, but it's doable with modern technology. Projects like Breakthrough Listen are attempting exactly this. The emotional journey of SETI researchers is also worth considering. Imagine dedicating your career to searching for something you might never find, spending decades looking at data, training algorithms, writing papers, giving talks, always hoping, always disappointed. How do you maintain motivation? How do you avoid burnout or cynicism? Different researchers have different strategies. Some focus on the journey. They find satisfaction in the work itself, the observations, the analysis, the incremental improvements in technique. They don't need to find aliens to feel their work is worthwhile. They're advancing knowledge, developing technology, training students. That's enough. Others maintain hope through probabilistic reasoning. They look at the numbers, billions of stars, trillions of planets. Even if intelligence is rare, the sheer number of opportunities means someone should be out there. It's a numbers game. Keep looking and eventually you'll win. Still, others find meaning in the question itself. Whether we're alone. This matters regardless of the answer. Searching is how we find out. So the search has inherent value. Failure is possible, but the attempt is worthwhile. There's also camaraderie within the SETI community. Researchers support each other. They share the frustration. They celebrate small victories. A new telescope comes online. A new algorithm improves sensitivity. These aren't detections, but they're progress. They're reasons for optimism. The community sustains itself through mutual encouragement, through shared commitment to the quest. This social dimension is underappreciated. SETI isn't just lone astronomers staring at screens. It's a community of people working together toward a common goal. That community provides resilience, prevents isolation, keeps people going when results are disappointing. Looking forward, what can we expect from SETI in the coming decades? More of the same with better tools, more comprehensive searches, more sky coverage, more frequencies, better sensitivity. The technology will keep improving. The searches will keep expanding. But will we find anything? That's the great unknown. We might detect a signal tomorrow, or we might search for another century and find nothing. The uncertainty is inescapable. What we can say is that our ignorance is decreasing. Each observation narrows the parameter space. Each null result tells us something, not as satisfying as a detection, but still informative. We're mapping the landscape of possibilities, ruling out certain scenarios, constraining the prevalence and nature of technological civilizations. This is progress, even if it doesn't make headlines. The wow-wow signal will likely remain a mystery unless it repeats or unless we develop theoretical understanding that explains it naturally. Without new data, we're stuck with the data we have, and that data is ambiguous. It could be natural, it could be artificial. We can't tell. This is frustrating, but it's honest. Better to admit uncertainty than to claim knowledge we don't have. The signal represents a moment, a possibility, a hint. Maybe one day we'll understand it. Maybe we won't. Either way, it will remain part of SETI history. A landmark, the time we heard something we couldn't explain, the time we thought we might have made contact, the time we wondered if we were alone or if someone was out there. That wondering is valuable. It keeps us curious, keeps us searching, keeps us human. One final thought about the WOW signal and what it represents for humanity. We're a species that emerged on one planet, orbiting one star in one galaxy among billions. For most of our existence, we thought we were the center of everything. The universe revolved around us, literally. We believed Earth was fixed and everything else moved. Then we learned we orbit the sun. Then we learned the sun is one star among billions in our galaxy. Then we learned our galaxy is one among billions in the universe. Each step was humbling. Each revelation diminished our centrality, made us smaller, less special, less important. This progression from cosmic center to cosmic insignificance happened over centuries. It changed how we see ourselves, our place, our meaning. The WOW signal sits at the next step in this journey. Are we alone, the only intelligence, or are we one among many? If the signal was artificial, we're not alone, we're not unique, we're not the universe's only conscious observers. Someone else is out there. That's both humbling and exciting. Humbling because we're not special, exciting because we're not alone. The universe is richer than we thought, more interesting, more alive. This realization, if confirmed, would be as profound as any previous cosmic revelation. It would change philosophy, religion, culture, everything. It would be the next step in our long humbling, from center of everything to one planet among many, to one intelligence among many. That journey continues. The wow signal might be evidence we're taking that next step, or it might not. The uncertainty persists, but the question is clear, and the search continues. Thank you for exploring the wow signal with me. If this journey into one of the greatest mysteries in astronomy expanded your sense of wonder, a like or subscribe really helps the channel keep investigating these profound questions. And remember, somewhere in the constellation Sagittarius, 78 light years away, there might be someone wondering the same things we wonder. They might have sent us a message. We might have heard it. For 72 seconds, we might have been connected, and then the connection was lost. But the possibility remains. The mystery endures, and the search continues. Good night, and may you never stop listening for the signals that might change everything.